Okay, hello everybody. What is this?
Hello, it's me, Lady Ada, with me, Mr. Lady Ada, and we're the original show and tell crew doing show and tell. So you can see
Yeah, we got all sorts of stuff going on here.
my robe back there with fling goes on it.
Yeah, this show and tell is the show and tell right before a very special event this week. We have restarted AdaBox, so AdaBox 21
It's happening.
unboxing is at 8 p.m. right after this. However, we do show and tell every single week, 7:30 p.m. Eastern time. It'll be us or some of the Adafruit team where people come and show and share the projects that they're doing and more. And you also get a sneak peek of some of the things that the Adafruit team is up to. And that is what we are starting with this week. Scott, take it away. What you got going on?
Hello. Thanks for having me, and thanks for hosting. I'm going to try to switch cameras live here.
Whoa, risky.
To bench cam.
Whoa, bench cam.
So what I have on my bench is a keyboard. I've cannibalized some of the keys. Sorry about that. But what I have here is one thing that's been missing from CircuitPython for a while is support for the USB host Featherwing. So I've got an NRF52 feather under here, and these wires are just for debugging, so just ignore those. And then on the top, I've got the USB host Featherwing. So I've got the basics working in CircuitPython. So if you show my screen, I'll plug the keyboard in here.
Okay, live demo.
What we got here is every 5 seconds it's looking for USB devices that have been plugged in. And so I will plug it in, and hopefully it won't crash. And it shows that there's a USB keyboard.
Wow.
And I can actually type. I think it's going to crash if I Control-C it, which is what it did. That's why I haven't merged it in yet, because there is a bug there.
Oh, that's the DNA thing. It's like confused.
Right. So, and it's actually like thinks the key's down. So it's like, yeah, even if I Control-C it, it will keep sending like a space or something, whatever it's sending. So yeah, deinit is something I've asked Tat to work on. Otherwise, it's just spamming keys because something's held down. But yeah, I got pretty far with it, being able to enumerate. So that's good. And it did actually read like the Control-C I did from the keyboard as well. So yeah, making progress on that. That's for NRF right now, but it shouldn't be too hard. Before I make a PR, I'll at least do Espressif, and there was another one I wanted to do. There's a little bit of port-specific stuff that I got to do.
RP2040, 7051, both are.
RP2040, yeah, that's what I was thinking of.
Okay, well, yeah. Look forward to it, because we can do USB hosts with RP2040, but it requires like all the PIO, and it's very
right.
It's okay, but I would prefer to use this chip, because then you can plug it in any feather.
Right.
Oh, I'm looking forward to this. Is cool, because in the poster for CircuitPython 9 has a keyboard. It's like USB.
I was going to ask you about this. So to bring this all together, CircuitPython 9 is out.
Yay!
Celebrating, kind of like being able to cobble together your own computer with all the different peripherals and more. So this is part of that.
Yeah, this is part of that. So right now it's in CircuitPython 9, it's only on the RP2040s. You can do native USB host, and then on the IMX you can do USB host as well. Not the 1011, but the higher end ones you can do it as well.
Yeah, the 1060 I think has a second port.
Yeah, it has a second port. And with this Featherwing, we'll have it there too. It won't. I think when your user code's done, we'll deinit it, so you won't be able to like use the keyboard outside of the VM, unless the board has it natively instead. So we'll see.
Okay, cool. And then on Fridays, people can tune into either you or Tim for deep dive, and we talked about some of this stuff.
Yeah, I was just thinking about what I'm going to do this week, and that's all dependent on health of my family.
Yeah.
And daycare. But yeah, I wanted to do kind of a recap of 9.0, kind of everything that went into it, and then cover some of the stuff that I'm thinking for 9.1 and early 9s after that, because I'm out of bug hunting mode for the minute at least.
Yeah, we had a big bug hunt, but now we're like time for new features, new chip.
Yep.
All right, very cool. Well, we'll be tuning in either way on Friday, 2 p.m. Pacific, 5 p.m. Eastern.
Sweet.
Thanks so much, Scott.
Thanks for having me.
All right, Jeff, what you got going on this week?
Hello. So I've been working for a couple of weeks on the Adafruit flopsy board, and I just wanted to show what I've been up to. This has been in Arduino, which is a little bit of a learning experience for me. I mean, I thought, oh, I programmed C++ professionally for years. I'll just go through this like putter. But there's a learning curve there. So kudos to all of you who are like good at Arduino or even just get stuff done. But anyway, this is the flopsy board with the display on it, and this is a 3.5-inch floppy disk, and it is running my custom firmware that I've written in Arduino. This is mostly up on GitHub. There may be one little bit that isn't. But when there's a floppy inserted and it sees the index pulse, it will rotate the little logo. So when I flop it, when I flush it, when I eject it, it says no media and it stops moving that. And then I can take and insert a different piece of media. And you probably weren't paying attention, but this one will say 720 kilobytes because it's detecting what the type of media is by actually reading the data on track 0 and decoding it. And it also will track whether the floppy is read-only or read-write. So here I've covered the write protect tab, so it should say that it is not read-only when I put it in.
Okay.
Whereas this one here, the write protect tab has the gap, which means it's protected. And when I plug it in, it'll say read-only. So it's tracking all that information from the disk. And if this was hooked up to a computer, mine's not right now, I'm just powering it here, it will appear as a USB drive of the right size of the detected media. And on Linux, even if you swap disks, it will Linux will understand that change and say, oh, that floppy went away, now I've got a 1440 KB floppy. So cool. It's pretty cool. Also tells you which track inside. So there's like a lot of information packed onto this screen. And yeah, just continuing to figure out kind of what we can do with this. Also runs Grease Weasel great. We got that working, and it works with 5.25-inch discs. But this is the disc that fit in the frame, so this is the one you get to see.
Yeah. Okay. Yeah. Not the 8-inch floppy yet.
I think this is
not the 8-inch floppy. No, that is back there.
The the physical deterioration of a lot of the removable media, it's starting to happen. It's coming up. So we're decades in. So if folks want to do archival work and save a piece of computing history in a variety of ways and share it, this is probably going to be one of the best, easiest, and open source ways to do it.
Mm-hmm. Yeah, this is not like with the Grease Weasel firmware, it's a really great archival thing. This firmware is more like I want to kind of have the experience of using a floppy drive, but I wouldn't use it for archiving. I'd use the Grease Weasel firmware, but it does run on this board as well.
It is really good though if you're like, oh, I just want to make a DOS boot disk or floppy. It's like you want to use.
Yeah, if I want to put some floppies, definitely. Yeah, I have a friend who he has an EEPROM burner that only works on his old 286 laptop. And it's like a whole thing to even get the files to it. So I will be getting him one of these.
You would love this. This is going to be great. Yeah.
All right. Thanks so much.
That's what I got. Well, thanks for that.
All right. Thanks.
All righty. Erin, what you got going on this week?
I just launched a new tutorial with these beautiful little LED Chinese lanterns. So they're just little paper lanterns. They got a little NeoPixel ring inside, and they're all wired together using a ESP32 Feather and running LED effects, which is a really cool LED sound reactive software. So I have a little video here of them in action. I'm just hit play.
Nice.
And as the sound reactive is really good. I didn't have to do any coding for this. The LED effects, actually, it just runs from my computer over Wi-Fi. And I have a whole bunch of pre-made animations that are, with sliders that are customizable and adjustable. So you can kind of tweak the animation to go with whatever song you've chosen.
And this guy, I just made this guy live too, by the way, because I was like, I know you're going to show up.
Good.
Yeah, so it just went live 5 minutes ago, so I'm going to blog it up in just a minute, but this is a pretty cool tutorial, and my favorite thing about it, it's like a giant art installation that fits in a shopping bag, right? Because I can fold it all up and switch it.
Yeah, they compress.
And yeah, so it's pretty fun. It was a lot of soldering, but it is, the materials other than, the Chinese lanterns are pretty cheap, and it's just the sound reactive software it's some of the best I've ever used. I've played with a bunch of them, and none of them are very good, but they're getting there. And this one I really like. It's open source. It's hello sugar bear. It's open source and free to download. So definitely check it out.
All right. Thanks so much, Erin and Cat Assistant. Bye-bye. All right. We're going to go to Rick, and then we're going to go to nanographics. Rick, what you got going on?
Hi, I have astronomy is my hobby, and one of the problems that it presents is, of course, weather. Weather is a big problem if the weather is bad. So I have an allsky camera, and it's mounted on the side of the observatory, and it basically just looks up and takes pictures all night long. It takes like 1,200 pictures during the night. And one of the things that it does is it gives me a picture of the night sky. So here's an example where you can see the Milky Way coming up, and it just tracks this all night long. Of course, the real reason I use it for is to see approaching weather, so I know when to either not go out or shut things down.
Yeah.
So what I did is humidity is a big problem, and if it's high enough, dew will form on the dome of the allsky camera, and then of course you can't see anything. The allsky camera has a heater in it, but it's just a power resistor that heats up, and you either plug in a 12-volt power supply or unplug it. And that's not a good thing because cameras are very heat sensitive, and the hotter they get, the more noisy they get. So you really don't want to just turn it on or off. You want to control how much power goes to it. So I made a heater controller out of a Wi-Fi M0 feather, and then this right here is a 433 megahertz receiver that I'm using to pick up transmissions from a wireless temperature and humidity sensor. So then the program that I'm running in here, which is Arduino based, is reads that humidity and then sends pulse width modulation to this MOSFET right here, and it controls the amount of power that's going up to the heater. So I plug in 12-volt power supply here, and this is where the cable goes up to the heater in the allsky camera, and it will actually control the amount of power that it's sending. And this is the sensor that I'm using. It's made by Accurite, and I made this little enclosure for it, but it's mounted on the side of the observatory, so it's reading temperature and humidity. Now, the other thing I'm doing is I like to monitor how things are going. So I'm also running a web server on the Wi-Fi portion of the M0. And all the web server does is when you interrogate it, it just outputs the data that it read from the sensor. So you get temperature in C and Fahrenheit, the dew point, humidity, and the heater power.
That's humid.
Pardon me?
That's very humid, 96%.
Well, it was, it was foggy at that time.
Wow.
When I took and did a screen capture. So, and I'll show you how that works. So I also wrote a little program, Python program that runs on a computer that just interrogates the M0 every 5 minutes and then logs the data to a CSV file, which I can then load into Excel and graph.
Yeah.
So what you can see here is you have temperature in C and Fahrenheit, and this blue line here is the humidity. So this is when the fog started moving in, and it got very, very humid, and then eventually passed out. So what the program in the M0 does is that at 70% humidity, it starts turning on the power going up to the heater, and it maxes out at 95%. And it's just a linear ramp between the two values. And then as the humidity goes down, it'll reduce the power or go back up. So it just tracks the amount of power that it sends to the heater. And I determine these values experimentally, where I would use more power or less power and see if it worked good at keeping the dew off the dome or not. And these are the values that I settle at. And then as the humidity drops down, it'll just reduce the power back down to 0. So it works really well, and I can't see any effect in my allsky images from the camera overheating, which I had been able to before I started implementing this power control. So it works pretty nice. And just to show the device again, so it's the the Feather M0 Wi-Fi. It's mounted on sockets, so I can plug it in and out of the proto board here as needed. And the same with a 433 megahertz receiver, but the MOSFET is soldered in.
All
This is
right.
an awesome project.
Outstanding.
I love
and,
this.
And really good presentation with everything.
I know you came with graphs and data.
And here's the Milky Way. And here's
so cool. And it's interesting because no matter where you are in the country or the world, like you're gonna need special tools to make the most of this equipment. I just love that you're like, hey, I'm just gonna cobble together something, but like this is like, scientist, engineer, maker, ingenuity.
Yeah.
Make something go, and you're like, you don't want to spend thousands of dollars. You're like, what do I have in the house that'll just solve this issue for me? So cool.
And it's just fun making it yourself too.
Yeah. We do have a user guide area on learn.adafruit.com. If you click playgrounds, if you ever want to put it up on there so other people can try to build it, go for it.
I think that'd be. Okay. I see like some people in the chat who are like, I need this for my scope.
Yeah.
And they're talking about their scopes.
Feel free to put it there, and we can feature it and all that.
Okay, and what I really do is take pictures like this.
Ooh, that's so beautiful.
Which galaxy collision is that?
Yeah, that's M51, the Whirlpool galaxy, and of course it's 2 interacting galaxies. So
wow.
It's
I've always lived in cities, so I'm very jealous.
That is a fantastic.
It's fantastic.
Yeah.
It's the NASA, as good as the NASA Hubble images.
Well, not quite, but I have fun.
Yeah, the homemade cookies are better, right?
There's James Webb, and then there's Rick Young. All right.
Okay. Thank you so much, Rick.
Okay.
Awesome.
All right.
So that was big.
That was the big.
And now we're gonna go small.
Yeah. All right.
Nanographs.
Adam, what's going on?
Hey everyone. I don't have a telescope here. I have a microscope, so I guess we're going the exact opposite direction. I have
we're gonna go to the quantum now.
Not quite with this one. We hope to get a microscope and explore the quantum soon. But
okay.
Cool. So SEMs are surface science, transmission electron microscopes, where it's basically an SEM on top and then an SEM on the bottom, and the sample's in the middle, and you shine the electron beam through the sample. Those are for exploring quantum. So I'm going to share my screen here real quick. I've got a accelerometer in here. There we go. That should be going now.
Yeah.
Okay.
All right.
So we're doing a little bit of beam finding at the moment here because I just got the sample in. So we are going to ask the age-old question in electron microscopy: why can't I see anything? Move something around a little bit. Okay, we're definitely looking at something because I moved the stage and the brightness changes. And I change the focus. Something's changing. But I'm not getting quite as clear of a beam as I would have expected to be getting. Make sure my electron gun's aligned. Sure I'm scanning, which looks like I am. Oh, I know what the issue is. I have to wiggle the magic card. There we go. Okay. One of the cards in the backplane needed to be wiggled. There we go. Okay. So we've got here a MEMS accelerometer. So this is a piece of silicon that has been very carefully crafted into an accelerometer. We don't really very frequently make things that spin in silicon, but traditional accelerometers or gyroscopes, they're always like spinning objects, right? So we, instead of spinning, we substitute just vibrating back and forth, and that kind of works out to be the same thing as spinning, more or less. So this is a, can you all hear me okay?
Agitated
Yep.
parts.
We can hear you.
Okay,
Keep
cool.
going.
So we've got a, so this is a 3-axis accelerometer here. So we have an X, Y, and a Z sensor. So this one right here is as oriented. This is going to be the Y-axis accelerometer. The one in the middle here is the Z-axis accelerometer, and the one on the right here is the X-axis accelerometer. So these plates right here, or I guess to start with, the big sections you see in that have all the holes in them, those are the those are what actually like vibrate back and forth. So this whole plate right here with all these holes in it, it moves back and forth left to right really quickly, and it gets actuated by we can see the plate with the holes in it has these fingers attached to it that kind of stick into this comb structure here. And so we use electrostatic forces to drive this. So if you charge it in one direction, it'll attract or repulse. And then if you flip the polarity, it'll go the other way. And so at the same time that we're driving it in that direction, we're also kind of sensing how much work it's taking to move it in that direction. And as the accelerometer moves, if the accelerometer is moving, say, to the right, then it will, the driver of this accelerometer will be able to sense that it takes more work to push the proof mass in one direction versus the other direction, and it can use that to determine, like, hey, I'm having to do more work to the left than to the right, so I know this whole accelerometer is like moving to the left. And that kind of works the same way for all 3 axes. So this is the Z-axis proof mass. And so this one just vibrates up and down. And so its capacitive drive and capacitive sense is done between the, like underneath this whole surface. And and this whole thing is allowed to vibrate or enabled to vibrate by it being mounted on these silicon springs here. So these 2 rectangles here, those are rigidly mounted to the silicon. And then we can kind of follow this really thin piece of silicon all the way around. So it goes like there and then back this way. And so that's long enough and skinny enough that that piece of silicon can flex without breaking. And then we can move over to the Y-axis accelerometer. This one's built very similar to the X-axis accelerometer, except it's just rotated 90 degrees. And so we can zoom in on here. We can see the sense in the drive combs. And then the part that is rigid right here. So this square without any holes in it right here, kind of in the middle of the frame, that is rigidly mounted to the silicon. And then as we move up here a little bit, we can kind of follow this, like, you can follow this back and forth. And this whole structure here is, again, another like silicon spring that lets this thing move. So for whatever reason, probably from some damage incurred during decapsulation when I took this one apart, we can see that the spring on the top here is fully compressed, while the spring on the bottom here has a lot more space between it. So it's decompressed. And we can also look at the distance between the combs, and we can see that they're not really even. There's like kind of, it looks like we're a lot closer to the bottom side than we are to the top side right now. And so, yeah, that's a MEMS accelerometer.
In school, we had to make 3-axis accelerometers, and the way we did that, because you could only get 1-axis accelerometers, is we made this little like 3D PCB sculpture where we had 2. You know, we had one on, like, it's basically a cube, and we had mounted a 1-axis on every side.
Yeah.
And they were analog output because they didn't have digital output ones yet. But I specifically remember like building them, and they were $20 a piece. They were really expensive. And you had to be really careful. You didn't want to break them. They were in a ceramic body too. It was
really fancy ones.
Very well. It was like, this is all you had. It was like very early, and so they were used, I think, a lot for like military and aerospace, because like nobody else, like no cell phone was going to put a $20 accelerometer in their, you know, like nobody was using it. So it was basically used for aerospace and military applications and industrial applications. So yeah, they were these ceramic and gold packages. I think it was called the ADXL 301. It was like one of the first ones, or ADXL 100 or something very early. It'd be cool to get one of those and take them apart, just to see, how have we improved on the manufacturing of accelerometers in the last, 20 years. I'm old.
Yeah, I think.
Keep coming back. You'll see the quotes in the chat and everything. Everyone liked the segment, and we get some fan mail afterwards. People email Adafruit and they're like, "I really like that segment on Show and Tell." So,
oh, cool. Oh, glad to hear it.
Yeah. So keep coming back and let us know if there's some parts that we have that you want to.
Yeah, absolutely. I'll have to look through the catalog and see what you all got. I was just like kind of browsing my parts, and I found all the ones that I took apart several years ago. But I'm like, I think we've got more than like a BME 680 we can put under here. So
you got the good ones. I mean, the AMG 8833. If you want, we can send you one of the. There's like a 64 by 48 thermal camera. We can send you one of those.
Ooh, that would be fun because we've been looking at the AMG 8833 a lot, but that is
it's only 8 by 8.
Only 8 by 8, right? So it would be very curious to see what a not 8 by 8 one looks like. So because they like really got away with a lot with those thermistor wires, just run wires and measure the resistance of the wire. And I kind of don't think that scales as well at the smaller sizes. So I think they moved to some different type of semiconductor devices.
Is there a part number if you move to the south a little bit? There was like something etched on the silicon.
Yeah. So the lid of this package used to be where all of this kind of like goop is, and I just like heated the package up with a torch and then dropped it in water, and that like thermally shocked it in half. And then these were all of the bond wires that went up to the digital control die. So I'm seeing, let's see here. I have scan rotation on right now, so my axes are not linear anymore.
Whoop.
Okay, let me turn scan rotation off so I can like actually drive normally. There we go.
Whoa.
Yeah, I'm gonna give you 30 more seconds because we're gonna bounce to do the AdaBox unboxing, but keep at it.
L33A.
Excellent. L33A, yeah. So there is a MEMS accelerometer. And so in my last little seconds here, I'll show you what happens when you try to clean one of these in an ultrasonic cleaner, even just for a second. MEMS accelerometers are very sensitive to ultrasonic cleaners. You can just if you shake them too hard, you physically damage the drive mechanisms here. So you can see one of the sense fingers has come out. So this is the second one I decapped. The first one I decapped, I ran in an ultrasonic cleaner for like 10 seconds, and it like sheared off like all of these. So they were just like all gone completely. This one I did it for about a second to clean it up, and I still like broke one of them. So don't put MEMS devices in ultrasonic cleaners. That's not fun. And we can kind of see how like deep the etching is here. So
yeah,
amazing.
All right, well, another fantastic show and tell.
Yeah.
Thank you so much.
Thank you so much. It was great showing off an accelerometer.
Yeah.
Thank you.
All right, everybody, that's show and tell. That was amazing, from the big to the small, from the bright to the keyboard to the
USB host.
Yeah, to the floppy disk. So we'll see everybody next week. AdaBox unboxing starts in just a minute or so. We will see everybody later. Thanks for joining us, for making this the best half an hour of the week every single week. This is Show and Tell. Bye, everybody.
Bye, everybody.